Welcome. In this presentation, we are going to talk about how to run a host application with an RTL kernel. First, we will start with a brief overview of the Amazon AWS F1 platform, the OpenCL execution stack, and of the SDAccel development environment. After this overview, we are going to have a closer look at some of the important aspects of OpenCL language. We will review the SDAccel environment, and finally we will look at the execution model of OpenCL and review some optimization techniques to improve performance. Let's start with an overview of the AWS F1 Platform Model. Here's an abstracted model of the AWS F1 platform. On the left-hand side, we have the software stack running on the x86 CPU. On the right-hand side, we have the hardware components of the FPGA. On the host CPU, the custom application interacts with the FPGA using the OpenCL API. OpenCL is an industry standard providing clear semantics for parallel computing. The OpenCL runtime is responsible for managing and servicing the various acceleration requests sent to and from the FPGA. At the lowest level, the drivers handle the PCIe transfers between the two devices. The FPGA comes preloaded with the necessary logic to DMA the data into the local DDR memory. The custom acceleration kernels can then be read to this data. The custom acceleration kernels can then read this data, process it, and write it back to the DDR using the standard AXI interfaces. OpenCL is an open industry standard for programmers to execute on heterogeneous systems. A system typically comprises of a host CPU communicating with other processors which act as compute devices for acceleration. The compute devices can be other CPUs or GPUs or DSPs, or as with AWS F1 FPGAs. The OpenCL standard is managed by the nonprofit Kernels group. OpenCL is both a language for expressing kernels, which describe the function to be performed by compute devices, and a series of APIs used to control the execution of the kernels on the compute device. For example, APIs are used to load kernels, transfer buffers to and from the device, and generally schedule operations and events. All the low-level management, for example, drivers talking to the PCIe interfaces, is orchestrated and taken care of by the Xilinx OpenCL runtime. The SDAccel development environment developed by Xilinx allows users to develop, debug, and analyze designs targeted for FPGA acceleration on the AWS F1 platform. Full automation of the entire flow from host code to FPGA acceleration is provided. This is fully supported with associated debug and performance analysis features at every step of the flow. All this is provided in an Eclipse-based environment, which is already familiar to software developers, allowing easy access to analysis reports and graphics from the GUI. We'll cover these features in more detail later in this training. Now that we have the foundation on the key aspects of this development flow, the platform, the language, and the development tool, let's start diving a little deeper. First, let's look at some of the aspects of OpenCL which are important to this development flow. As noted before, the OpenCL framework allows programming in heterogeneous systems. We've seen that it separates the host code from the device code or kernel to be accelerated. This already captures some of the parallelism inherent in the algorithm. The kernels can be computed independently of the host code. This functionality also enables a number of other useful options. Software running on the host can be used to run any number of kernels. This allows for the building of very scalable systems. An important aspect of OpenCL is that it's very portable. The kernel code and the host code should work with little modification across devices. However, performance is not portable. Some devices will accelerate more efficiently than others. OpenCL also supports vector data types in the kernel code and asynchronous data movement in the host code. This allows large data sets to be easily specified and moved. And users can use blocking or non-blocking calls for the majority of the data movement. Non-blocking calls are useful to prefetch data or schedule data transfers ahead of time to minimize device execution time. With OpenCL on FPGAs, things are similar to other OpenCL implementations on CPUs or GPUs. An exception is the compile time to build the application. In the CPU or GPU flow, the kernel code is compiled on the fly. On an FPGA, the process to create custom hardware takes longer. For this reason, OpenCL API CL create program with binary is used. This allows FPGA kernels to be created in advance and then simply loaded at runtime. As the example here shows, CL create program with binary is used to load the pre-built binary. The CL create kernel function is used to reference the kernel. And after setting the input buffers, which is not detailed here, we would launch the kernel with the CL enqueue task function. The flexible OpenCL infrastructure lends itself very well to executing kernels on FPGAs under host control. Now, let's look in detail at the SDAccel development environment. In this section, we are going to give a detailed overview of the SDAccel IDE. Then, we are going to talk about the hardware emulation flow and its use for debugging. We are also going to review the performance analysis reports and finally talk about the hardware execution flow. As discussed earlier, the SDAccel Integrated Development Environment, or IDE, allows users to develop, debug, and analyze designs targeted for FPGA acceleration. Being Eclipse-based, the IDE has a very familiar look and feel to developers and allows them to easily manage their projects, use different perspectives to develop and debug their application, and easily manage the software emulation, hardware emulation modes, and hardware execution modes. Note that in the context of RTL kernel, there is no software emulation mode available, as the RTL kernel can only be simulated in the hardware emulation mode. Finally, the IDE GUI allows the user to review the reports, profiling an application timeline to further understand the readiness of their design for their performance needs. As noted earlier, in the OpenCL execution model, there are two independent execution paths. The host code and the kernel code execute on different devices. There are also two associated compilation paths, one for the host code compilation into a host code executable performed using GCC or G++ and linking against an OpenCL API library, and another path for the kernel compilation into a bit stream to program the FPGA. This second path to compile the FPGA executable is performed using the SDAccel compiler XOCC, as talked about in the previous module, on packaging and integration. As with other Eclipse-based IDEs, SDAccel makes use of makefiles under the hood to automatically handle the dependencies. This diagram shows an under-the-hood view of how the RTL kernels are compiled in the SDAccel environment. RTL designs are first compiled into a Xilinx object file, or XO, using the RTL kernel wizard. The XOCC compiler takes the compiled kernels and the target platform definition to assemble the design. If hardware emulation is desired, the emconfigutil utility is used with the host code to create an emulation executable. If the target is to run on the FPGA, the XOCC compiler compiles the kernels into an FPGA bitstream. First, let's review the hardware emulation flow. The hardware emulation flow is entirely a software-based flow and runs without the need to be on the AWS F1 instance. In this flow, the hardware is modeled in a cycle-accurate manner. This flow is fast and yet allows detailed analysis of the hardware implementation. RTL kernel developers may even view detailed simulation waveforms using the hardware emulation flow. This flow is ideal for verifying the functionality of the device and for reviewing further opportunities for optimization such as data transfer and kernel execution rates. Debug support is also provided in the hardware emulation flow. Given our standard view of the host and the FPGA accelerator, debug support is provided through GDB on the host, and debug support is provided through detailed RTL simulations of the custom hardware on the kernel. This allows even the most complex behaviors to be quickly analyzed in great detail. Again, the communication functionality over PCIe is modeled but not simulated. The SDAccel development environment also includes a profile report. This report provides details on the efficiency of the kernel and the data transfers. Information is provided as explicit values. For example, 100 bytes per transfer or transfer of 4 megabytes. And as percentages, for example, a transfer efficiency of 40% tells us only 40% of the bandwidth is used. The profile report also provides profile rule checks, or PRCs, to highlight areas of concern. Perhaps only a few bytes of data were transferred, or perhaps the kernel is not called very often by the host program. In either of these cases, like others, the benefits of acceleration may be limited with the current configuration. The PRCs highlight suboptimal aspects of the kernel implementation and point you to areas where the solution may be further optimized. Note, the kernel and the data transfer rates are only available after hardware emulation. The application timeline provides a graphical view of the performance. This shows events of interest over time, such as when host OpenCL API calls occur, the start, stop, and duration of the data transfers, and the execution time of the kernel, including when it starts, stops, or pauses waiting for data. This quick means of visualizing the performance of the application allows you to quickly focus on the areas of concern. In an ideal high-performance system, most of these tasks should overlap in time, maximizing throughput. After optimizing the application using the hardware emulation, the system flow may be run on the FPGA. This step has the longest compile time and should be run once you have satisfied with the performance reported in hardware emulation. However, running on the actual hardware means this step is also the fastest to execute. Once the system flow completes, the same profile summary report may be analyzed. The numbers provided after execution on hardware are 100% accurate. This flow is also the final step in verifying the implementation of the accelerated kernels. Do note that the AFI must be created before running on the F1 instance. Now let's turn our attention to the OpenCL execution model. Understanding this allows you to easily understand how data moves through the system. Here is an overview of the OpenCL execution model. As you can see, we will review everything from device power-up and initialization through all data transfer steps, executing the kernel, and obtaining the results. Let's look at each of these steps in detail. On power-up, the FPGA is loaded into the shell. The shell automatically communicates to the host when it's ready for use. The host program can now start to create an OpenCL context. This consists of registering the platform and the FPGA device and opening a command queue to start servicing the device. When the host code executes the CL create program with binary API, the kernels are loaded into the device. On the AWS F1 instance, this binary executable calls the AWS secured storage. And the Amazon FPGA image, or AFI, is loaded on the FPGA. Note that this is without any end-user intervention nor access to the bitstream being downloaded. The kernels are now ready to be executed on the FPGA. Next, the application needs to start sending data. The first step in sending data is to allocate buffers on the device. In this small example, 3 buffers are shown. 2 are used to send data to the kernels, and 1 buffer is used to store the result. These device buffers mirror buffers already allocated on the host, where the input data is already stored and where the output data will be stored. The function CL_EnqueueWriteBuffer API is then used to copy data to the device. Note that the naming convention is that this is an enqueue operation for the host and that the operation is to write a buffer from the host to the device. If the kernel has multiple data inputs, multiple CL_EnqueueWriteBuffer API functions calls are used. Note there are other ways to transfer data from host to device, as multiple API variations are available. The Xilinx GitHub shows examples for those ways. The buffers are then associated with the kernel, and the kernel is started using the CL_EnqueueTask API. The kernel then executes, it reads the data from the input buffers, performs its calculation, and writes the results back to the output buffer. When the kernel completes operation, it automatically notifies the host. The kernel done signal is registered in the command queue. If CL_finish was used, this would have been a blocking call, as this waits for the command queue to complete all operations. Now, the CL_EnqueueReadBuffer function API is then used to transfer data from the DDR back into the global memory. Again, the naming convention is as before. This is an enqueue operation for the host code, and that the operation for the host is to read a buffer host to the device. Notice the use of the synchronization function CL_WaitForEvents, which is also blocking and enforce the synchronization with the read event. If we didn't use it and try to read the host buffer too early, it would contain the previous data and not the updated data from the device. This completes one complete execution of the kernel or kernels. After reviewing this OpenCL execution model, you can now appreciate how the device operation is sequenced from the host code and how data is moved through the system. We can now look at the host code in more detail. Now that we reviewed the OpenCL API and provided a high-level description of the key steps of an application executing on F1, we can now dive deeper into the host code and OpenCL APIs. We'll start with an overview and then review the typical APIs one would use. As we saw in the last section, there are 3 main actions required from the host code: setting and registering up the FPGA device, executing the kernels, including setting up the data transfers, and verifying or saving the results and releasing the device once the application completes. It's worth noting that the host program generated by the RTL kernel wizard contains all of these steps. Let's dive one level deeper and review these APIs in detail. This shows the basic steps for setting up an FPGA device. The first API call is used to interrogate the system and discover which platforms are available. Note, it's good coding practice to use error checking after each API call. For debug and productivity reasons, this is something to be encouraged. Once you know what platforms are available, you can then select a device and set up a context and command queue with which to control the execution. Notice the platform ID is used to create a device ID, which is then used to create a context, which is in turn used in the subsequent API calls. The executable binary is then read from disk and loaded into the FPGA with the CL_create program with binary. The next stage is to begin executing the kernel or kernels. This process starts with creating a kernel, as we saw in the previous section, start to allocate the buffer for the data. This process starts with creating a kernel, as we saw in the previous section, start to allocate the buffer for the data. In addition to setting up the buffers for the data, scalar arguments may also be set. These would be inputs to the kernel, which do not change dynamically during the kernel execution. The CL Enqueue task API is then used to enqueue the start of the kernel execution. Kernel execution will start as soon as all dependencies are met. This is most often transferring the input buffers associated via the use of CL set kernel arg. Finally, note synchronization is used here. CL finish and CL wait for events are used first to wait for the completion of the kernel so that we can start reading back data, and second, to wait on the completion of the readback. Another synchronization could have been used, for example, to associate an event to CL Enqueue task upon which CL Enqueue read buffer would be dependent as an input. The final stage of the host program is releasing the memory and kernel. The CL release program API must be used to allow profile information to be accurately collected. A productive host program is one which checks the data sent back from the kernel to verify that the data is correct. This may seem like an additional step, but it greatly helps to debug any issues. The host program matches the execution model we saw earlier. Set up the device, execute the kernel, and release the device. The host program, main.c, created by the RTL kernel wizard, is a good starting point from which to develop your own code. It contains all of the basic steps for executing a kernel on the FPGA. You're highly encouraged to review additional resources for more information. The SDAccel design environment tutorial provides an overview of the functions and flows in SDAccel. The optimization guide provides techniques for writing high-performance code, and the video Fundamental Concepts of Application Code is a good quick reference for more details on OpenCL host code. Now that we have reviewed the host code with graphical examples and some further details during the host code review, let's review some of the host code optimizations that we can do. When trying to understand the application performance issues, we need to identify the source of the issue. It might be the kernel itself that is not as fast as the designer thought, either due to the kernel's microarchitecture or because of something else in the data path or memory. It might be the host code that is the bottleneck by not saturating the PCIe, for example. Or it might be the overall integration of the whole host and kernel accelerator that is not performing well together. We can use the performance reports and application timeline from SDAccel, as we already described, to help us understand what's happening. However, by understanding the design, we can sometimes see potential issues. So let's start with a simple example. Let's talk about moving the data efficiently to and from the device DDR to the host or the kernel. As we know, there's an inherent latency overhead when accessing DDR due to the inherent DRAM technology used. In this bad example application, a hypothetical kernel would process a single pixel. The operation performed are the same as we saw before. The host would send data over PCIe to DDR, the kernel would read it, process, then write back. Signal to the host that the kernel is done, and the host would pull the pixel. This process would repeat for all of the pixels in the input image. We can understand that all the latency overhead for one pixel are really penalizing the performance. Let's see the solution, which is somewhat obvious for most people. So the solution is to use buffers to do memory transfers and send data in bulk rather than infrequently whenever this is possible. On the host side, using a buffer will mean that the runtime will transfer that buffer over PCIe, and so the driver will initiate a burst. Note that to get good throughput over PCIe, a size of 1 megabyte is preferable. It's okay to use less, except that you must remember you might not get the maximum throughput or bandwidth. On the kernel side, use buffers, and to make bursts, make your accesses on the AXI master on consecutive clock cycles. When using RTL kernels, you need to pay attention to the handshaking signals. When using OpenCL, C or C++, you need to use pipelined loops to achieve bursting. To maximize the bandwidth usage, on the host, use large buffers as much as possible. The practical PCIe limit is around 8 gigabits per second. And on the kernel side, with 512 bits at 250 megahertz, peak throughput would be in the range of 16 gigabits per second, a bit less in practice when accounting for refresh, idle times, etc. Finally, if more bandwidth is required, a kernel could use more DDR banks, as 4 DDR banks are available on the AWS F1 platform. This obviously would be a trade-off with any other kernels present in the FPGA active at the same time. Let's take an example kernel that simply reads from the AXI master interface into DDR, does some process, and writes back to DDR via another AXI master interface. The application timeline could be as the one shown here. However, we can notice that the kernel isn't always executing and there are big gaps. If we use task pipelining, we could schedule ahead of time the transfer of the data for the subsequent executions before the kernel needs it. This could be achieved with the API CL-Enqueue migrate Mem objects rather than using CL-Enqueue write buffer. Now we can see that the kernel is executing almost continuously. This is the execution time saved. As the last comment for this slide, and as a thought exercise, we can see that the kernel execution time would be the bottleneck. It is the one that is the longest and the fullest. The other data transfers have gaps. If we were to reduce the kernel execution time, the performance would improve again, but the data transfers would become the bottleneck. Taking into account the learnings from the previous slides with buffers, burst, and task pipelining, there could still be several kernel enqueue, and this is still causing an overhead in dispatching the commands and arguments to the FPGA via PCIe and other scheduling tasks. In order to reduce that overhead, we need to consider if even larger buffers or contiguous memory can be used in order to minimize the time spent for management. For example, with image processing, a kernel would process more than one frame per enqueue, say a batch of 20 images or anything fitting the design. In the situation of many input scalar parameters, instead of using CL set kernel arg multiple times, we could put those parameters into a buffer and transfer those in a burst. Another approach to improve throughput is to use several kernels in parallel. This is beneficial when a single kernel doesn't maximize or saturate the bandwidth and when resources are still available on the device. A suitable situation is when less than 50% of the bandwidth is used, so 2 kernels make sense. However, if 60% of the bandwidth was used by one kernel, it might still make sense to use 2 kernels, knowing that the theoretical need would be 120% of the bandwidth. That is impossible, but we would achieve near 100% utilization in practice. The ratio 100 over 120 would mean the 2 kernels are each 80% utilized, or 83% utilized. We show 2 possible implementations of the command queues which should behave similarly. This last slide about optimization is an advanced topic which requires more host code changes. Suppose a kernel or a set of kernels in the FPGA can process several workloads in parallel. Only one software process can access the FPGA at any one time. In order to maximize the FPGA utilization, a client-server host application can be used to ensure that the client process can submit workloads to the server process. In turn, the server process will dispatch workloads to the FPGA. This scheme makes it possible to have several client processes accessing the same FPGA for the same task on different datasets. Let's wrap up what we have just learned. This tutorial focused on the host-side application development using an FPGA accelerator. It provided an overview of the host application using the OpenCL framework, introduced the SDAccel development environment designed to streamline the development of the FPGA-based software accelerator, showed the development of a host application starting from an initial prototype and concluding with an overview of host-side algorithm optimizations. Thank you for watching.